Welcome to the session on integration, area under a curve or under the x-axis. The objectives for this session are to find the area bounded by a curve and the x-axis. Recall the rule for integrating kx to the power n. If f dash of x equals kx to the power n, then f of x equals k over n plus 1 times x to the power n plus 1 plus c, where n does not equal minus 1. When integrating polynomials, apply the rule for integration separately to each term. If f dash of x is the derivative of f of x for all x in the interval ab, then the definite integral is defined as integral from a to b f dash of x dx equals f of x between a and b, which equals f of b minus f of a. Let's look again at the steps for integrating definite integrals. Write the definite integral statement with its limits, as shown, then integrate and write the integral in square brackets, as shown, and finally evaluate the integral by working out f of b minus f of a. The area of the curve can be found using definite integration. Consider a positive curve y equals f of x and define the area under the curve to the left of x as a function a of x. So here's our curve, it's positive. Consider the point x and the corresponding point where it meets the function at f of x, and the area under the curve to the left of x, which is denoted by a of x. Now, if x increases by a small amount, say delta x, the area now changes to a of x plus delta x. As x increases, the area a of x also increases to a of x plus delta x. For a small increase in x denoted by delta x, area increases by the amount delta a, which equals a of x plus delta x minus a of x, as shown in the diagram in blue. Now the change in area is approximately rectangular. So as delta x is made smaller, any error will be insignificant. Therefore, delta A is approximately equal to the width times the height of the rectangle. In other words, delta x times y, or y times delta x. And if we rearrange this, we obtain delta A delta x is approximately equal to y. Now, if we take the limit, so as delta x tends to 0, we obtain dA dx equals y. And integrating gives us a equals integral of y dx. Now the area between a positive curve, the x-axis, and lines x equals a and x equals b is area equals integral from a to b y dx, where y equals f of x is the equation of the curve. So diagrammatically, it will look something like this. We've got a positive curve, f of x, and we've got limits a and b, and we've got the shaded area in yellow beneath the curve. Let's take a look at an example. Find the area of the finite region between the x-axis and the curve y equals 15 minus 2x minus x squared. Pause the video and have a go. Press play when you're ready to view the solution. So let's solve this. If we factorize this function, we obtain 3 minus x times x plus 5. The intercept with the y-axis is 15. And the curve crosses the x-axis at x equals 3 and x equals minus 5. Therefore, if we're wanting to find the finite region between the x-axis and the curve, we're looking for the region between minus 5 and 3, which is below this curve. So area equals the integral from minus 5 to 3 of 15 minus 2x minus x squared dx. And so integrating this term by term, we obtain 15x minus x squared minus x cubed over 3. And then putting in the limits, so x equals 3 here, and x equals minus 5 here. And then tidying up, gives us 8 1/3. Now let's consider the area below the x-axis. The area between a negative curve, the x-axis, and lines x equals a and x equals b is denoted as minus the integral from a to b of y with respect to x, where y equals f of x is the equation of the curve. Since the curve is negative, notice in the diagram that it's below the x-axis, and therefore we're looking for the highlighted region. And that is why the integral has a negative sign in front of it. Let's take a look at an example. Find the area of the finite region between the x-axis and the curve y equals x squared minus 7x plus 10. Let's solve this. Factorizing gives us y equals x minus 2 times x minus 5. And the curve will look something like this. And the region we're looking for is the region shaded in yellow as shown. The points of intersection with the x-axis are x equals 2 and x equals 5. So here's x equals 2 and here's x equals 5. And therefore the area that we're looking to find is minus the integral from 2 to 5 of x squared minus 7x plus 10 dx. So let's integrate this term by term. The first term is x cubed over 3. The second term is minus 7 over 2x squared. And the last term is 10x. And of course we're integrating between the limits 2 and 5, and we have a negative in front of the brackets. So plugging in the limits, x equals 5 here and x equals 2 here, gives us the expression shown. Of course, we can now tidy up, and tidying up gives us this expression, which is equal to 4.5. What happens if the area is above and below the x-axis? If the area straddles the x-axis, the region is split into the area above and the area below the x-axis, and we calculate the integrals separately. So as you can see from the diagram, we have that the region from 0 to a is above the x-axis, and the region from a to b is below the x-axis. This is why area is equal to the integral from 0 to a of y with respect to x minus the integral from a to b of y with respect to x. And of course we've subtracted that because the second region is below the x-axis. Let's take a look at an example. Pause the video and have a go. Press play when you're ready to view the solution. So let's solve this. We are required to find the area of the finite region bounded by the x-axis and the curve y equals x plus 2 times x minus 1 times x minus 5. A sketch of this will look something like this. The curve intersects the x-axis at the points x equals minus 2, x equals 1, and x equals 5. As you can see, the region between minus 2 and 1 is above the x-axis, and the region between 1 and 5 is below the x-axis. So when we calculate the area, we integrate from minus 2 to 1 of y dx minus the integral of 1 to 5 of y dx. And we denote that by I1 minus I2, as shown. The first integral, of course, is I1, and the second integral is I2. This is I1. We've plugged in the expression for y. And this is I2. Again, we've substituted in the expression for y. So let's calculate I1. We've of course expanded the brackets so that we can integrate easily. And if we integrate term by term, we obtain x to the 4 over 4 minus 4/3 x cubed minus 7 over 2x squared plus 10x. And of course we're integrating between the limits minus 2, 1. And we plug in x equals 1 as shown. And then we subtract this expression with x equals minus 2 plugged in as shown. And tidying up, that gives us 22¼ So I1 equals 22¼ Now let's find the area I2. Again, we've expanded the brackets so that we can integrate easily. And again, integrating term by term, and plugging in the limits. Here's x equals 5 plugged into this expression, minus the same expression, but with, of course, x equals 1 plugged in. And if we tidy this up, we obtain minus 53 1/3. And of course, this makes sense with what we see in the diagram. We have a negative number because this region is below the x-axis. And of course, now that we have the values for I1 and I2, we can simply plug these values into our formula for the area. Area equals I1 minus I2, which equals 22 1/4 minus 53 1/3. And tidying this up gives us 75 7/12. This brings us to the end of this session. If you have understood its contents, you should be able to find the area bounded by a curve and the x-axis. Thank you very much for listening. To understand this topic in greater depth, do attempt the exercises in your textbook related to this topic.